Hello, welcome to my quick little video on materials, starting from where we left off at the end of GCSE with Hooke's law, and then going into Young's modulus and how we can use all of these things to compare the properties of different kinds of materials. So let's get straight into it. Okay, so what's Young's modulus all about? Let's start with our classic Hooke's law formula from the GCSE. F equals K, and I'm going to call it delta X. That's the extension, that's the change in size. Now, this formula is fine, it works quite well for springs, but the problem is that the spring constant actually depends quite a lot on the size of things. Small springs and big springs and more tightly coiled springs will have very different spring constants. So let's try and make this to be a formula that only depends on the materials and not the sizes of things. The force that you exert on an object depends on the cross-sectional area that force is spread out over. Something thick is going to be able to withstand a much bigger force than something thin. So let's divide out this area dependence and say force divided by cross-sectional area. That's kind of more interesting than force. That's called the stress, which is denoted by the Greek letter sigma. That's still going to be proportional to the extension, because the cross-sectional area is assumed to be a constant, but again, something long is going to stretch by more than something short. So let's divide out the length. Let's say the change in length divided by the original length. That's the strain, which is denoted by this curly E, Greek letter epsilon. And like I said, they're still proportional, but the constant of proportionality is no longer the spring constant, which depended on size and shape and a bunch of other things, but it is capital E. That is Young's modulus, which only depends on what material you're looking at. So that's Young's modulus, which is, okay, capital E, we already said it, depends only on material. Now, what about units? The stress sigma has units of pascals because it's a force over area. Strain has no units, meters divided by meters, which means that Young's modulus must also have units of pascals. Cool. And if we compare these formulae, we see they look very, very similar. We still have forces proportional to extension in both cases, just with some slightly different stuff thrown around. So from now on, we'll be thinking about the formula stress equals Young's modulus times strain. So let's see how this is applicable to different materials. Now, for most materials, you remember from GCSE that force or stress this time. So instead of force on the vertical axis, we're going to have stress in pascals. And extension, except this time instead of extension, we have strain. So that's epsilon, which is like the fractional stretching. A strain of 1% means it's stretched by 1/100th of its original length. At first, they're directly proportional to each other. And the slope, the gradient, the initial gradient rather, is Young's modulus. You'll remember that spring constant sometimes is also called stiffness. So the Young's modulus tells us how stiff something is. You'll also remember that we had something called the limit of proportionality. And if we go beyond that, we're no longer directly proportional. So the graph starts to curve. Now, this graph is quite complicated. I'm going to draw it first, but then I'll explain it in a way that I understand it. So what happens is first it stretches quite a lot. You'll see the strain increases even though the stress doesn't increase by much. So without increasing the force by much, it stretches a lot. Imagine playing with a piece of blue tack and suddenly it gets a lot softer as you stretch it. What then happens is it gives way. So this point here at which it gives way is called the yield point. Somewhere before the yield point, it has crossed the elastic limit, which means that anything above this point is not going to return to its original shape. So after the yield point, it suddenly gives way as you get some rearrangement of the atoms and molecules that make up the material. After that point, though, it starts getting stiffer again. That's something called strain hardening. Until you reach the absolute highest stress that you can withstand. That's your ultimate tensile stress. Ultimate. tensile stress. After that point, the material fails and you have your breaking point, which is also the ultimate strain. That's the biggest strain that it can have, the most it can possibly stretch. Now, how do I think of this graph? I like to think about someone in medieval times being tortured on a rack. So their feet are tied at one end, their hands are tied at the other, and you've got a rope going around a winch like this, and you've got a horrible executioner pushing down like that and stretching this person. So let's see what's going on. At first, the more you pull on him, the more his body stretches. And then at some point, he reaches the elastic limit beyond which he's going to be taller forever. The yield point, I think of as the shoulders popping out of their sockets. You know, there's literally a rearrangement of how his body is. And so he's going to suddenly give way and get a lot longer, even if the force isn't that much bigger. After that point, though, we get some strain hardening where now you're starting to stretch the muscles and tendons and the skin and everything else. And he's going to reach the highest force that he can possibly reach until finally you get what's called necking. His body starts tearing in half and eventually it just gives away completely. So pretty horrible mental image, but it's quite useful for remembering what's going on. Now, we can use this graph to categorize different materials with some key words that you may remember from GCSE chemistry. So I'm going to color code these. Something brittle is something where the breaking point happens before anything else. So that is a brittle material. It breaks very, very suddenly. Normally, with most materials, you know when they're about to break because they'll get thinner, they'll get softer, all of this other stuff will happen, yield point, strain hardening, ultimate tensile stress, and that. Brittle materials don't do that. They have a region which obeys Hooke's law, and then they just break. Something that's stiff, well, we already said that Young's modulus is the stiffness, so it will have a very high Young's modulus. It will have a high initial gradient. So our brittle material was also stiff, but let me show. Here is a stiff material. Whatever happens afterwards, so that might happen, but it's initially stiff. Something strong has a very high ultimate tensile stress. That means it can withstand large forces per unit area. So this is a strong material, high UTS. Something that's ductile is something that can be easily stretched. That means that it might be quite soft. It's not going to be particularly stiff, but its breaking point is going to be at extremely high strain, right? So that means that you're going to get very, very, very large extensions, even with relatively small forces. One last little thing about these graphs. You may remember from GCSE that the area under a force extension graph was the energy, the elastic strain energy that is stored in a material. Well, in this case, what we have on the axes is not force and extension, it's force per area, the stress, and extension per length, which is the strain. So how does that help us? Well, remember that energy was something like, if it's an area, it's going to have units of y-axis times x-axis. So the energy is going to look something like, well, in fact, it was half of force times delta x, right? Well, now with these axes, we don't have half f delta x as the area. The factor of a half, by the way, coming because often what we have is a triangle, so it's half times base times height. So instead, we have half times force over area, that's the stress, times extension over length, that's the strain. Well, the half fx is still there. So it's still an energy. So that's what we have here, an energy, but then A times X, that's your cross-sectional area times your length. That's actually the energy per volume. So that kind of figures, right? Because the whole point of dividing the force by the area was to get something that doesn't depend on the size of the material. Same with the strain. We divided the extension by the length, so it doesn't depend on the size. So we have the energy per volume, which doesn't depend on the size.